Alright, going to do these problems that are examples of work done by a variable force. So 34, I've got a little graph. I'm just going to make a sketch of that. It's acceleration versus position. And it goes like this. And the scaling is, let's see, that is 8. Here and here the acceleration is A as 20 meters per second squared. Alright, that's 8 meters. So I got a 10 kilogram brick. Moves along an x-axis. Its acceleration as a function of its position is shown. Scale of the figure's vertical axis is 20 there. What is the net work performed by the brick by the force causing the acceleration? So, well, I know that work is equal to the area under a force versus position graph. So that would be great if this was that graph, and it can be in one simple move, because all I have to do is multiply this acceleration times mass, which would make this 200 instead of 20, because mass times acceleration is that force, and that turns it into this. And then I just have a triangle that I need to find the area of. So the area of that is going to be 1/2 base times height. So that looks like it's going to be 800 joules. Cool. The number 35, some people just call it 35. I like to call it the number 35. The force on a particle is directed along an x-axis. It's given by this. Force is equal to F sub 0, that's like a constant, times x over x sub 0 minus 1. That's intimidating looking. Find the work done by the force in moving the particle from x equals 0 to x equals 2x sub 0 by plotting fx and measuring the work from the graph, and then by integrating. And I think I'm going to, let's see, depending on exactly where you are in your calculus class, you may or may not know how to do that. I guess I'm just going to do it, and then if it's over your head and you're like, what is he doing? Then don't worry about it. Definitely we could do it by plotting this. Now, before I plot this, I am not super crazy about the way that this is written, so I'm going to distribute this f sub 0, and that's a constant, right? F sub 0 over x sub 0. That's a constant times x minus f sub 0. So now I think I can see more clearly. This is just a line, and its intercept is negative f sub 0, and I'm going to scale it like this, because x sub 0 is this, that's the only constant position that I know that they're giving in the problem, and I think they want to know how much work is done getting to 2x sub 0. So, let's see, what's this? How do I graph the rest of this line? Well, the slope is f sub 0 over x sub 0. That's rise over run. So that means if I go over x sub 0, it goes up f sub 0. So it actually goes through right here. You could also just plug x sub 0 in and see that you get 0. And so it looks like this. Right, that might remind us of some kind of like spring, right, where that's the equilibrium position, and similar to that. All right, and what do they want? Oh, they want to know what is the amount of work done from here to here. Well, it's 0, right, because that's got that symmetry here. So the work done is from 0 to 2x sub 0 is 0. So that's doing it by graphing, part A. Now part B, if you know how to find antiderivatives, you know what the fundamental theorem of calculus says and all that, then, since we have this written like this, let's see if we can do it that way. So I'm taking the integral from 0 to x sub 0 of, this is just a constant, times x minus, that's just a constant. So the antiderivative of some number times x is some number over 2 times x squared. And even if you don't know exactly what's happening here, I'm going backwards. I'm taking the antiderivative, and you can always just check to see, okay, if I took the derivative of this, derivative of number times x squared, the 2 would come out to the front, and I would cancel that out, and I would, in fact, get that. And then what's the antiderivative of just a number? It's just that number times x. So when you think about what would the derivative of this be, well, it would just be that constant. So that's what we're doing there. And then I plug this in, so 2x sub 0 over 2x sub 0 is 1 times that squared minus f0, oops, oh sorry, I think I messed that up, didn't I? So I should be plugging in this 2x sub 0 squared, one of them cancels out, and I get f sub 0. The other one doesn't cancel out because I'm squaring that, so that's 2. That would be this, minus, when I plug this in here, f sub 0 times 2x sub 0, and then minus, what do I get when I plug the 0 into these? They both have x's in them, so a whole bunch of nothing, and that is in fact the same term, so I get 0. So anyway, whichever way you do it, you get 0. And no worries. If this B, if it's just a little bit out of your calculus reach right now, that's okay. And if that all made sense, well, that is certainly also okay. 36. Excuse me. Another graph. Lots of pictures with these ones. Let's see. This time I have a force versus position, and there is an axis here. And the Fs, the scale is 10 newtons, where that Fs is. This is 10 newtons, and these go to, and then by the time we get to 4, it's dropped down to here, and then I'm going to chill out here at 0 force, and then go down to -5 here. Sorry, should have made that axis a little bit longer, and that's at 8 meters. All right, and we've got a 5 kilogram block. Moves in a straight line on a horizontal frictionless surface under the influence of this force, excuse me, that varies with position as shown in this graph. The scale is how much work is done by the force as the block moves from the origin to 8 meters. So from the origin to 8, that's moving the right way in terms of finding our area. So I just need to find all of this area. That's it. And this mass actually didn't matter, did it? So let's see what we got here. This is 2 by 10. That's 20 joules of work there. And then that looks like half of that. Right, that triangle's half of that rectangle. And then I have here, this is 2 by 5. So looks like 25 joules will be that area. All right. Now, listen, the calculus is pretty much the easy part of this physics game, isn't it? It looks like here I've got another one of these acceleration versus position graphs, and the scale of the acceleration is AS is equal to 6 meters per second squared, and the mass is 2. So I'm just going to get right down to business here and go ahead and multiply this whole axis by the mass and turn it into a force versus position graph, because that's what we want. So I'm going to try to do my best to make a little sketch of this. My graph's a little sketchy there. Okay, so we need to find the, I'm presuming we just need to find the, oh, we need to do a bunch of different areas. Okay, so let's see. This is from 0 to 9 here. So this is at 1, this is at 4, this is at 6, this is at 8, and this is at 9. All right, so let's see. We want this. How much work has the force done on the particle when the particle reaches? This is from 0 to 4. So 0 to 4. How much area do we have there? 0 to 4. Let's see. This is a 3 by 12. That's 36 joules for that rectangle, and then I've got a 1 by 12. So maybe that was the answer of the whole universe and everything or whatever from the Hitchhiker's Guide to the Galaxy. The answer was 42. Maybe this is the question. So let's see, B, we want to go to 7. So if I'm going to 7, I have this, that's my same, well, this is 0 to 4 right here, so I could, 0 to 4 is 42 joules. I don't have to redo that. And then this, from 4 to 6 is 0, and then from 6 to 7, I've got a negative area, that's a 1 by 12. So 42 minus 12, it's going to be 30 joules there. And part C, we want to go to 9 meters, the whole direction, the whole way, the whole direction, let me just say that. So that is the 30 joules, that's going up to 7, and then I got another one of those minus 12 blocks, right, from right here, and then I got a half of one of those minus 6, so that looks like 12 joules. All right, so what is particle's speed and direction of travel when it reaches those different points? Well, work, oh, I guess we are going to need the mass for this, aren't we? If this is the only force acting on it, then work is equal to the change in kinetic energy. And this thing started from rest. So that means the work, total amount of work done is equal to its final kinetic energy. So let's see what we can do here. We have in part D, is it the same for 6, 7, and 9? It is. So how much work got done here? 42 joules got done. That's going to be equal to 1/2 the mass. What was it, 5? Nope, 2. 2 times V final squared. So V final is equal to looks like the square root of 42. So it's 6.5 meters per second. That's all in the positive direction, so the positive direction of the x-axis. Part E, same thing. Now I have 30 joules, and that's going to be equal to that. So that's about 5.5 meters per second. That network was also positive. Never gets to negative, right? Because this negative area, that's going to be slowing it down, but there's still positive work done here. Last bit, let's see, can we tuck it over into this little corner. 12 joules is equal to 1/2 mv squared. So VF there, still positive. It's going to be the square root of 12, which is 3.5 meters per second in that positive direction. And that's it. Pretty easy stuff. Hey, I had to show you this cartoon because you might be, like, now that you're like doing a little bit more calculus in physics class, I just want to show you, there's my feet walking. I want to show you this cartoon, which not everybody can understand, but now maybe you can. See the guy all stressed out, Physics 122 t-shirt? It's a reoccurring nightmare, Doc. I dream I'm in this class where calculus is the easy part. Ha ha ha.